introduce our next speaker. He is Thomas Fitzkee, and he is going to talk about mathematics and why sunshades for autumn. I think he is from Benedict, France.
Hello. Thank you all for having me. I'm going to talk a little bit about mathematics and maybe something that you might deal with every now and then in hot South Carolina. It's related to the paper by Curtis Fice and Ramin Nadi. It won the George Polly, award for MAA, and I thought it was a really good paper because I actually understood most of it and not just the first few pages or paragraphs after the introduction. So I was quite happy that I understood it and thought, well, if I can understand it, then surely decent undergraduates can understand it too. I don't really consider myself that much smarter, just more education. So we'll start out with some definitions, and here we can pass around a few of these. Small sunshades, otherwise known as frisbees. So it might be interactive. Oh! All right. Oh, yeah, close.
No, just like baseball game, you gotta get
All right. Found out why we were doing mathematics and not NFL, right? All right, so the one thing you might notice, which I didn't notice until I read the paper, is the sunshade has a metal wire or band around the outside. Now, it's not just the regular wire, it has a band. And it can be twisted this way, but does not like to be twisted this way. Okay? And this will be considered open position, and then you can twist it into other smaller circles. And so this is the closed position. Now the one thing to note is that in open or closed position, anybody get back into closed? You notice if you follow the band around, it's not twisted. Okay, the band goes around and around and around. There's no twisting like this. Okay? Probably cut your finger or something like that if you try to twist it this way, but you can twist it around this way, but not in this direction. Okay? And we're going to call the two outside edges boundary circles. And just imagine that we put a little dotted line in the middle of the band going the whole way around. And we're going to call that band the core of the band. Now, the boundary circles on the outside are solid curves, and the core of the band is the dotted one kind of in the middle. All right, let me define the braid. A braid consists of one or more strands of string starting at the same height and extending downward and ending at the same height. Of course, with mathematics, we want some crossings of the strands of string. Otherwise, you just have strings going straight down, and that's kind of boring. So here we have 4 strands and 1, 2, 3, 4 crossings. And you see that the natural way to show a crossing is one line stops and goes underneath and then comes out on the other. And here we have 3 strands, 1 crossing, here 3 strands, 5 crossings. And you can probably notice by looking at the 2 on the right that knowing the number of strands and crossings does not define the braid, because the last 2 are actually equivalent. All you have to do is pull this one out and put it on the side, and you pretty much get the 3 strands, 1 crossing. So knowing the number of strands and crossings does not automatically define the braid. All right, what we're going to do after we have a braid, like here, we're going to connect the tops to the bottoms in pairwise fashion so that we can kind of close it up and get what you might know as a knot. Okay? Now, when you close the braid, you may wind up with more than one component. Okay? Meaning if I start like right here and I follow the string around, I'll traverse the whole closed braid. Right? It's just one. Yeah, it's just one braid. Okay? If I follow this around, this is like, if we call this 1, 2, and 3. If I go down here, I come around, now I'm in this like second position. I follow that around. I go to the third position. I follow that around. I come back to the first position. But if you look at the closed braid on the right, you might not notice you have more than one component. Can you separate them? You see the first one is a component in of itself. And you might notice that the second, third, and fourth kind of are all one component. Yeah. So one component braids and two component braids. All right. We want to draw these closed braids in kind of a uniform way. You notice we have 4 crossings. To be in the braid, for a braid to be in braid position, what we're going to want is only one crossing to occur at a horizontal position. Okay? And there's a way we can fix that. So right here, we have 2 braids, 2 crossings occurring at the same horizontal position. So what we can do is just extend these 3rd and 4th strands down, extend them down after the second crossing, and then do the 3rd crossing, and then likewise extend the 4th crossing down. So at each horizontal position, we only have 1 crossing at a time. If we do that, then we're in closed braid position. Great. Okay. First kind of fact statement. With the sunshade in closed position, the core of the band is a single component closed braid in braid position. So, of course, if you have it like this or like this, it's only one component, right? Otherwise, because you only have one frisbee or sunshade. So it's got to be one component. And put it in closed, put it in braid position. As you can, what we did before is if it's not, then we just extend the strands as needed to get it in braid position. All right, if we consider a closed braid consisting of M strands and N crossings, so 3 strands, 2 crossings. If the closed braid is composed of a single component, then M and N must be of opposite pair. Okay? This kind of comes down to permutations a little bit. This you could say 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay? And in order to have like a complete cycle in permutations, a number of letters and a number of kind of crossings have to be of opposite pairs. Okay? And you know that's true. So this is one component, 3 strands, 2 crossings, so opposite parity. Opposite parity, everyone know, One number is even, the other has to be odd. So here, 3 strands, that's odd. So in order for this possibly to made up of one component, it has to have an even number of crossings, in this case 2. And you notice in that other one, which we already looked at, it's 2 components. It has 4 strands and 4 crossings. So just by determining that, without following the strands around, just by determining we have 4 strands and 4 crossings, we're going to note that we have more than one component. Again, in the case on the right, we have 2 components. All right, so statement 2, with the sunshaded closed position, if the band is coiled into N loops, and the core of the band is N crossings, and M and N have to be of opposite parity. Yeah, so we know we got one component, and I don't really want to give it away, but when we fold it up into closed position, you know you have, I don't want to say it, but you have, like in that case, 3 strands. And if I were to cut it and bring it on the bottom or something like that, you can see that I have 3 strands, and we can't quite see how many crossings. Okay, but the number of crossings and the number of strands have to be of opposite parity. Otherwise, we would have in some way snuck 2 things in. Okay? So, but we only have 1 sunshade or 1 frisbee, so we have to have opposite parity for crossing and strains. M and N must be of opposite parity, right? All right, another definition we want to look at is the length. Now, the length is a set of N continuous loops in space. Okay, so this is another kind of application of knots. We want to take the different components and maybe in some cases leave them separated. In another case, put one inside the other, and then, you know, after that, mathematicians get crazy. Right? It's not interesting unless it's a little bit crazy. Now, once we have a link, the hard part is determining when one link is different from another link. And that's where we come up with this invariant called a linking number. Okay? Now, a linking number, we're only going to look at for 2 components. Okay? And here's how we determine the linking number. We're going to orient each component with a direction by putting an arrow on it. And if it's right-hand oriented, now I'll just demonstrate this in a little bit. We're going to write a +1 by the crossing. If it's left-hand, then we're going to put a -1. Okay, we're going to do this right hand or left hand, a +1 or -1 for each crossing between one component and another. We're not going to do this if the component crosses itself. Okay? And then we add up all the +1s, -1s, divided by 2 and take the absolute value. And again, the reason why we look at this is because this is an invariant for knots, for links, so that we can say one link is definitely different from another link if it has a different linking number. All right, so I already put the pluses 1, -1, so let's see. First, I'm going to put a blue, so I'm going to orient them by putting arrows. Okay, so this one component is going around this direction. Okay, this other component is going around this direction. All right, and now what we want to do is we want to put a pointer finger on the component that's on top in the arrow direction, and try to put our thumb in the other direction, and we have to see if we want the thumb to go that way, in which case it's right hand position +1, or this way. So if I put my hand up there with my pointer finger on the blue, because that's the one on top, and my thumb on the maroon, would I need to use my right hand or my left hand? And I gotta put my palm on the screen. I did this one time when I was doing students like this, and they were, you have to do it like this, correct? So that's a right hand position, so that's a +1 for that crossing. So the blue, of course, goes for the direction for the component on top, and the maroon for the one underneath. That's another right-hand position, correct? So you see why this would be a left-hand position? Because I want my pointer finger to go down because that's the strand on top. And then this is going to be going that way. So that's why I'm going to need a left-hand position. That's why it's a -1. Okay? And do you remember why we don't do a +1 or -1 there? Because we're not going to do a +1 or -1 when a component crosses itself. So we only do this when one component crosses another component. Because we don't want to put a + or -1 here, right? Because we could just undo that easily. We don't want that to affect the linking number. So the linking number of this link is, let's see, we got 3 +1s and 1 -1, add them up, divide by 2, absolute value, so this linking number is 1. Right, cross crossing, so we don't assign a + or -1 there. So, any idea what the linking number of this might be? 0. And what do you think about that one? That one might be a little bit hard to figure out until you remember that a linking number is an invariant. That's 0 also, right? Because this link is actually the same as this link. It's just written in 2 space differently. And I think that linking number is 1. Yeah, linking number 1. And of course, we want this linking number to be different than 0, right? Because it's a different link. So as I said, linking number is invariant. That's why we get linking number 0 for both of these links, because they actually are the same link, just represented in 2 space differently. And it doesn't matter the direction because we're taking the absolute value. So you're free to write down his errors however you want. All right, in statement 3, with the sunshade in closed or open position, the linking number of the boundary circles is 0. In open position, this is pretty much what our boundary circles are looking like, right? So that means when we do this, it's the same link. Since the linking number is invariant, the linking number for this in closed position also should be 0. All right, so now let's look at the linking number in closed position. So let's see, consider the boundary circles of the sunshade in closed position, and suppose we have M strands and N crossings of the core band. Okay, so we're looking at the core band, and it has N strands and N crossings. And since we cannot twist the band this way, there's going to be no self-crossing of the boundary circle. So if I could twist this, then one boundary circle would cross the other without the core of the band crossing, but that can't happen. So the only way we're going to get the boundary circles to cross is when we have a crossing of the core of the band. All right. And so, of course, we have 2 boundary circles. So I try to designate one as a dark line and another as a lighter line. And the center is the core of the band. And if we have n crossings of the core of the band, so this is one crossing of the core of the band, the dotted line crosses. You actually have 4 crossings of the outside of the band, right? But this one right here is where one outside, the same outside crosses itself. So that's a self-crossing, that's a self-crossing. So really, we only have 2 non-self crossings wherever the core of the band crosses. So if we have n crossings of the core of the band, that means there's 2 and non-self crossings between one boundary circle and another. All right, and now we want to find the linking number. So we're going to orient them by putting arrows. This is just to show that if you have 2 arrows going in one direction for the 2 boundary edges, when they go around, when they come back around, they're going to be going in the same direction. You can't have the 2 arrows going this way and then come back around and one's going in one direction and the other's going the other, the opposite direction. In this case, you're going to have a +1 and a -1. In this case, you're going to have 2 +1s or 2 -1s when you do the orientation. That would be a -1 and that would be a +1. Okay, so whenever we have a crossing like this, if we look at the 2 components, we're going to get a +1, +1, or -1, -1. Okay? Because that's what's going to happen here. +1, +1. Okay, but remember the linking number, we divide by 2. Well, I'll get to that later. That's going to help us out because we're going to get 2 +1s or 2 -1s. So when it follows that in each of the n pairs of crossings we have either 2 +1s or 2 -1s. All right. And here's what I was getting at. For each crossing, we're either going to get a +2 or -2, because you can't get a +1 with a -1 to give you a net effect of 0. All right. So if each of these crossings, in essence, is going to contribute a +2 or -2. All right. But then remember in our formula we divide by 2. So in each case you're either going to get a +1 or -1. All right. But if you remember, we said the linking number of this or this has to be 0. Okay. This is the linking number of this thing is 0. So if we twist it up, the linking number still has to be 0. Okay. But each crossing has to contribute a +1 or -1. So the only way you can add up 1s and add up -1s to get 0 is if half the crossings are +1, half of them are -1. Okay? But that would mean you have an even number of crossings. Half of them contribute +1, half contribute -1. All right, so we have an even number of crossings. Remember, the number of crossings and the number of strands have to be of opposite parity. So if we have an even number of crossings, we have to have an odd number of strands. And you know the number of strands is kind of the number of loops you have, which I think about the only way you can pull this up is with 3. Okay? So in closed position, the band of the sunshade must be pulled into an odd number of loops. So that's why sunshades fold oddly. Now with this one, I think it's small. Pretty much can only do it in 3. I've been told I haven't done it because I don't want to have to go out and buy a new one, but apparently if you want to do 5, you can fold it up into 3, and then you can try to make one of the circles be bigger than the other two. And you know, mathematicians just iterate the process. Try to make these two small, this one big, and just twist this one up into 3, in which case you'll have the 3 plus the 2 others, which will give you 5. Okay? But any way you do it, without breaking it, you have to fold it up into an odd number of circles. So don't try to force it into even, in which case you pretty much break it. All right, so some references. That's all I have.
Do you have any questions?
Yes. I'll ask one. It might be kind of silly, but is there some way to get an analytic representation of what you're doing by assigning a function? Or is that too far-fetched?
You might be able to, but kind of not theory, and all the strands and all that are made up, so you don't have to do analytic stuff. That not book is kind of made so you don't get into the analytical part, you get into the more visual parts, and hope that it's more understandable to undergraduates, even maybe students before calculus.
Any other questions?
I have a question here. Is there a theorem about the linking number being invariant, or maybe I missed that on the? How do we know is it invariant?
It's invariant because there's different ways you can change. You can change the link around that are allowed, and you show that the linking number won't change if you execute one of these allowed movements. They're called Reitenmeister moves, and the way it goes is the link doesn't change when you do these Reitenmeister moves, and if you can show the linking number doesn't change when you do these moves, then it's an invariant.
But there is nothing on literature written about this or anything.
Pretty much that first book is kind of the Bible about it all. But it's, as you can guess, it's kind of hard to write down what rules are allowed to untwist and what ones are not. For instance, you know, I mean, it's pretty obvious to tell that these two are the same, right? But trying to describe what sort of movements like that are allowed and what are not gets to be a little bit cumbersome. Y'all all right with, you know, you see what I mean? This one's going behind, so you can pull it over, in which case it would come straight down after that, in which case you have that one. So you have to show that all those allowed moves don't change the linking number. And, right, people that thought about this want to get away with the analytical way of doing things there.
Any other question? Okay, thank you again. Now we have again another 5 minutes. We will start another speakers.